Hi. Now, today I'm going to be discussing the concept of half-life, and half-life particularly in the concept of radioactivity. And if you watched my previous video, I discussed how radioactivity works, but I left the question open is, well, what is the rate of alpha decay, beta decay, and gamma decay? And that's a concept called half-life. But before we discuss half-life, I want to give you a little of a demonstration. And what I have here is a measuring cylinder and some beer. And if you may or may not be aware that when we pour beer, we get this layer of foam, often referred to as the head of the beer. But of course, over time, that foam size decreases. And the question I have for you is what is the rate at which that decreases? Is it a linear decay or is it an exponential decay and so forth? And what we're going to do is we're going to pour some beer in here, and then what we're going to do is measure the size of the foam by just simply looking at the gradations of my measuring cylinder, and we're going to do that with respect to time. And then what we're going to do is we're going to analyze the data. So let's have a look and we'll start the process going. So let's start the timer. And let's leave it on its own for a moment. So I think we've done a reasonably good job of measuring the time now. So now what we're going to do is we're going to measure the variations in the gradations here and plot that with respect to time, and we're going to put that into Excel. So let's have a look at how that comes about. So here I have a table that represents my data that I collected in Excel. So you can see I have the time, I have the bottom level, I have the top level, I have the difference, which of course is the height of the foam that I have. Now, just a little word of caution here, these values are approximate because I found it difficult to read the level of foam because it dragged on the sides, but it's relatively close to what the values would be. But now let's have a look at what the graph looks like when I graph this. So here I have my overall graph of the foam, and you can see it does not decay at a linear rate. It curves. So this curve, if I try to draw as best as I can a curve, you can see that we have this decay rate that looks something like this. Now, this is often referred to as an exponential decay. Now, what do I mean by that? Well, in this case, there is some sort of constant value by which this seems to decay at a rate, and that is the concept in our case of a half-life. Now, what do I mean by half-life? Well, let's say I started this value up here, and this is going to be my 880 over here. And let's have a look at roughly the time it takes to get to half that level. So that's about 44, so that's going to be about here. Now the time of that, if we tap that down like this, you can see it's approximately, let's say, 65 seconds. Now it's not precise, my curve here isn't really truly representative of the dots, but you get the point I'm trying to make. Now let's take the time it takes for half of this 44 to go down. So now we jump down to 22, and 22 is over here. Now again, this is a rough estimate, and if we tap that down like so, you're going to see I'm going to get a value of approximately 130. Do you notice that we have a lot actually disappearing in 65 seconds, but in the next 65 seconds, we actually get half of what we had previously. So the half-life is the time it takes for half to decay from the previous level. So we've gone from 88 to 44, 65 seconds. 44 to half of that, 65 seconds. If we then continue to the next slot, and half of 22 is 11, we're going to get a value that's roughly around here. It's not very precise, of course, and if I put the dotted line down like so, you can see I'm going to get a value of around 180. Now this is about 50 difference, and that's clearly because of my graph not being precisely drawn. So wouldn't it be great to actually determine the half-life here by doing some graphical analysis of this data, knowing that this is an exponential graph? Now, to do that though, we need to do a little bit of mathematics to give us an understanding of how to do that. This whole thing is called an exponential decay, and the formula that describes an exponential decay is that the change of the numbers that you have with respect to time is equal to negative lambda multiplied by your initial amount, which is our n, and this lambda is referred to as your decay constant. Now that decay constant can be different for different substances, but we're particularly interested in the term of the decay in terms of our half-life decay. So in order to determine that, let's have a look at how we rearrange this formula into another form. Now, it requires some calculus to rearrange this, and so I'm not going to go into that because really that's not the level of physics or mathematics that we are requiring. But if I were to use some calculus, I'm going to get a reformulation that says this, that n is equal to n naught e to the negative lambda t. Now, n is the amount that you have left over. N is the original amount. E, of course, is your natural log, negative decay constant, and then the time that has elapsed. So obviously we have different times that will give us different amounts to be left. So how can we incorporate our half-life concept, that is the half-life, which is the time for half your substance to decay? How can we incorporate that into this half-life? Well, let's say we just got half-life. So our n over n naught is going to be equal to a half, and that of course is equal to e to negative lambda t. But the t now is exactly one half-life. So we've got now e negative lambda, and we've got t of the half-life. That is our half-life for getting half to be left over. If I now take the natural log of a half, I'm going to get, that should be negative, I'm going to get negative lambda t to the half. Now because this is a half, then I can flip this, so to speak. So I get log 2 is equal to positive lambda t to the half. And now you can see that my term of lambda becomes the log, natural log of 2 over the half-life. And of course, that can also be written this way, that my half-life is equal to log 2 over lambda, which is my decay constant. Now, let's remember that. Now here, I have my same graph, but you'll notice here, I have now introduced a extra column, and that extra column is simply the natural log of n over n naught, which I've basically used from my values here. And you'll see they're all negatives. And then what I've done is I've graphed my time with respect to the natural log, and I get a graph that looks like this. Now, why is that? If I start off with that n is equal to n naught e to the negative lambda t, therefore n over n naught is equal to e to the negative lambda t, you can see now if I take the natural log of n over n naught, I'm going to get negative lambda t. But our negative lambda, our lambda of course, is our value of negative ln2 over the half-life multiplied by t. I now have a function here, that is, if I graph this with respect to this, I get a constant value, and that will represent the slope. So that formula becomes the formula of y is equal to negative mx. So my slope of this line, and you can see what I've done here, I've graphed the data here, and I get a lovely linear fit. My slope, which is this here, is my ln2 over the half-life. So now let's look at that mathematics. I'm getting the slope, which is 0.0128. That equals natural log 2 over my half-life, and if I then work out my half-life, I'm going to get a value of 54 seconds. So there is my half-life of my beer foam. To take 54 seconds for half of it to decay. Now, clearly there are a number of errors incorporated in this,
but it's the process that is really important.
Now, I examined the data of the larger measuring cylinder as well, and I discovered that its half-life, the time it takes for half of it to disappear, is actually a different value, and you'll see the results here.
And now I've saved time by just showing you the time here and my log natural here of n over n2. Here is my classic curved shape like so, my exponential decay, and here is my graph that gives me my linear fit, and you'll notice that my slope is now equal to 0.0027 negative. That is equal to log 2 over the half-life, and so my half-life of my larger cylinder of beer ends up being 257 seconds. So you can see a larger cylinder will give us a significantly larger half-life.
So in many respects, this models radioactivity pretty well. We have a half-life of our foam. Now, our foam, of course, is consistent of bubbles, and those bubbles are popping, and therefore the foam reduces in size. Now, when each of those bubbles pop and release their gas, that's a random event. It's spontaneous. We don't know when that happens. But nonetheless, we find that over time, that decays in, that classic negative exponential graph, and therefore has a half-life. Now, I repeated the experiment with a larger beaker, but in that case, the half-life was different. That is, the time it took for half of it to disappear was a greater value. So you could argue that I have two substances here with different half-lives, a shorter half-life and a longer half-life.
So now let's have a look at the radioactivity. So if I were to look at what radioactivity is, you should be familiar with the fact that ultimately we have a substance that decays into another substance, then releases some form of radioactivity. Now, what that means, of course, it can mean an alpha particle, a beta particle, or gamma radiation. So, of course, and I use my alpha particle here as an example. So this is our mass number and our atomic number. Then with, for example, alpha decay, we have 4,2 helium here as an alpha particle. And of course, this becomes A minus 4. And this becomes Z minus 2. Now I could do this also for beta particles and gamma radiation, but you can watch my previous video on radioactivity and I'll discuss that more. But the point is that we have this transmutation going on here. So if I have, let's say, a substance that is, and I'll make it nice, a circular substance here, if I am interested in the half-life of a substance, then in a certain half-life, then half of that here would transmutate into another substance. So let's say after one half-life, I have half of my original substance left and I have now half my other substance. Now, in the next half-life, I would have this amount decay, and so now I have a quarter, 2 half-lives have transpired. And of course, I can continue that on and we get that classic exponential graph that we have in terms of half-life. Now the half-life, of course, can vary from substance to substance. So for example, let's take an example of, let's say, carbon-14. So carbon-14 looks like this in terms of its relationship, and it, in this case, transmutates to nitrogen, and this becomes 7, and this becomes still 14, and it releases a beta particle, and of course also some energy, and of course our elusive antineutrino. Now the half-life of carbon-14 is 5,730 years. So if I have a certain amount of carbon-14 in the body, and it's a small percentage of the carbon in your bodies, then it really stays relatively constant because you're constantly taking in carbon through your food and so forth. But when the body dies, you no longer have the intake of carbon, and so the amount of carbon-14 is now fixed in your body, and over time, of course, that decays. And by measuring how much is left in your body in terms of carbon-14 and comparing that to the half-life of 5,730 years, you can work out the age. Now, at the other extreme, I have technetium-99, M. Now, technetium-99 decays into regular technetium-99, which is still radioactive, by the way, and releases gamma radiation. Now, referring to the technetium-99m, the half-life there is only 6.6 hours. So it's relatively short. And that's pretty helpful too, because when you, for example, do a technetium-99 scan and we utilize the gamma radiation that is coming off this transmutation, then we allow you to absorb some sort of technetium-99. It tags various things such as muscles and so forth, and as a result we can see some functional information by measuring the amount of gamma radiation coming from you in terms of gamma, using a gamma camera. However, you don't want this technetium-99m to be in your body for that long because it can cause damage. So a relatively short half-life is really important. So you may have certain micrograms of technetium-99m in your body, but within, let's say, 24 hours, you have a significant drop in amount of technetium-99m and therefore a huge reduction in the amount of gamma radiation that is going to come off it.
Now, some would argue if I start off with, let's say, 500 particles and over, let's say, its half-life, 250 transmutate, then why do not the remaining 250 transmutate in exactly the same time? Well, I want you to think about it this way. Imagine I have 500 particles and over its half-life, half of it decays, and I have 250. Now, let's say I put that away. Let's say now I have 250 particles to begin with, and I measure how long it takes for half of it to decay. I'm going to get the same time. Now, clearly, I started with 250 and have gone to 125. Now, over here, I had the second stage of my 250, and clearly they're going to be decaying at the same rate as this. In other words, it's independent of how much is decayed beforehand. So it's not a linear relationship of the decay rate, but a negative exponential relationship. So that's one way of thinking about it as to why you don't get all of them decaying in exactly the same amount of time in the second phase.
So now let's look at an example of calculation involving radioactivity. So let's say we talk about radon. Radon is a radioactive gas that is emitted by the ground, but we're not particularly worried because the amount that is released is relatively small. It has a half-life of 3.82 days. Now suppose in a basement we have 3 by 10 to the power of 7 atoms that are trapped there. How many remain after 31 days? Well, we have a number of things here. We have our half-life, we have our initial N naught value here, and we have the time. So if we now use the formula, we know that N is equal to N naught e to the negative lambda t. Now our N is what we're interested in. Our N naught in this case is 3 by 10 to the power of 7. We get E. Now we need to know lambda, and our lambda of course is a decay constant. We know that is the natural log of 2 over the half-life. So in this case we've got ln2 over 3.82 days. This is in days, so therefore the time that we're going to use here must remain in days as well. So that's okay to use days. You don't have to convert it to SI units so long as you remain consistent. So our decay constant becomes 0.181 days to the minus 1. Now we can substitute that in. We get 0.181, and of course this is negative, and now we multiply by a time which is of course 31 days. And when we substitute that all in, we get 1.1 by 10 to the power of 5 atoms. Now that's relatively straightforward when you are given them numbers, but let's say you have to work out the half-life of a substance, then you just need to remember that if I were to convert this formula here in such a way like I did previously into this formula, so the natural log of n over n naught, so in other words we have the log of one side is equal to negative lambda t, and of course lambda is our decay constant, so we get negative natural log 2 over the half-life, and of course all of that is multiplied by t, you can see now I am able to solve for the half-life if I know the initial and the final amounts and I have the time frame here. So that's another way of solving for variables within this equation.
Well, I hope that has helped you understand the nature of half-life with the analogy of the beer over here, but also in the real sense in terms of radioactivity, and that you now can apply the formula for half-lives to varying types of problems. I'm Paul from High School Physics Explained. Thanks for watching. Till next time, bye for now.